Hey guys, what is going on? I hope you're doing amazing. Welcome to another PyTorch tutorial. Today we'll finally be training our first neural network. First and foremost, the most important part of training a neural network is the data. The dataset that we'll be using is the MNIST dataset. Here's an image of the MNIST dataset from Wikipedia. So the MNIST consists of pictures of handwritten digits, as you can see here. The handwritten digits, these images have labels corresponding to the digit. So you can see the 0 will have a label of 0, and then the 1 will have a label of 1, and so on and so on. Pretty simple, right? So yeah, let's actually just get straight into coding. So first and foremost, I've imported Torch, Torch Vision, and Matplotlib. So with Torch Vision, we're actually going to have to import a transform called the 2-tensor transform. Let's just do that real quick. You can see it's over here. And this basically converts a PLI image into an ND array tensor, which is what the MNIST dataset is going to give us. It's going to give us a PLI image. So let's just make this transform quick. Transforms dot 2-tensor. Cool. Once we've done that, now we actually want to just load in MNIST. So we'll actually just call this DS for dataset. And that's also from the Torch Vision library. So we're going to import that and then MNIST. And we're actually going to check the documentation. So we want to specify the root and if it's trainable, but we don't know. I think it's by default it's the training dataset. And then afterwards, yeah, we have the transform over here, which is over there. Cool. So let's just do that. So we're just going to make the root the base directory, then we'll say train equals true, even though it's defaulted already. Then transform equals to tensor. Then we want to, yeah, I forgot the last part, which is we have to get the download equals true. Or else if you don't set this, it won't download the dataset. So let's just let that run so long. Cool, it's all downloaded. So let me just actually plot this. So when we get the data, so if you just go data of 0, and then we print that, sorry, not data, ds of 0, gonna get a whole lot of numbers, but you can see that it's ended in a bracket and a comma 5, which means that this is a tuple. So let's actually just split this up. So image comma label equals ds. Then let's actually just print the label and then print image.size. Image.size just gives the shape of the image. So the label indicates that the picture is of a 5, and then the image size, we can see it's a 28 by 28 image with just one channel, which means it's grayscale. If it was RGB, it would be 3. So yeah, let's actually just plot this. So plot this real quick, and then I'm just going to do image of 0. So when we want the grayscale, we just want to input like these two columns over here, or these two dimensions, and CMap, and just going to make this gray. Cool. Okay, once that's, so you can see it's a digit of 5 like we expected. So let's move on. Okay, so first of all, we're going to want to initialize the weights. And we're going to do that by just setting it to random tensor. So this is a 28 by 28 image, we're going to want to actually flatten it because the neural network only takes in a vector. It doesn't take in like a grid of values. So we're going to want to flatten this. So when we load in the data, but for now we're just going to say the first weights takes in a 28 by 28, not 28 by just a 1 by 28 squared image, and then we're actually gonna leave that like that. Then we'll do b1 is equal to torch dot rand n, and then 1000. So this is just equal to the n number of neurons. This would be the number of neurons inside the first layer. So that's the weights and biases from the first layer. Let's just do the second now. Torch dot rand n, and we got 1000, and we're actually this is gonna be our last layer as well. So we're gonna make that 10, which is 2. Since there's 10 different digits from the MNIST dataset over here, we're gonna have 10 different neurons to output. So, and that will be all good. And then lastly, we'll do the bias as, which is torch.rand n of 10, which is the same as this. Cool. So once we're done with that, we'll actually just copy these, and we actually have to set the requires grad equals true. Now what this does is it tells PyTorch, okay, we want you to actually keep track of the computations that are done on these tensors, and then that way we can backpropagate the loss and find out what the gradients of these tensors are, and then we can change the weights accordingly. And lastly, we actually want to do the learning rate, which is the rate at which the network will learn, but we'll dive into that a bit later when we actually use it. So let's just run this. Okay, now we're gonna get on to the training loop. So I'm just gonna put in some parameters so long. So this keeps track of the loss. This keeps track of the number of correct predictions, and we're gonna set that to 0 at first. So yeah, what's gonna happen is we're gonna loop through each data point, and we're gonna add this running loss, and we're gonna divide by the number of times that we iterated through the data, so that we can get the average loss. So next we're gonna have, we'll just do image comma label. Actually, wait, we'll do a step as well. Step comma, so in enumerate ds. So we're looping through the ds and we're enumerating. So the ds is going to give these two values like we saw above here, and then enumerate is going to give the at which point in the data we are at. So let's just, so once we have our image, we're actually going to want to flatten it. So what we're going to do for that is we're going to flatten it, we're going to basically make it a 2D tensor instead of a 3D tensor. So what we're going to do is we're going to just change the shape of it by specifying the view function. I'm going to set that to 28 by 28. Well, 28 times 28. So this makes it, instead of 28 by, this would be what it is originally. We're going to change it so that all these things get put into one kind of like row or column. So once we've done that, we'll actually put it into neural network. So we'll have torch. So we have x is equal to x, and then times the first weight plus the second bias. And then actually after that, we're going to want to put in like a ReLU. So we're just going to type ReLU there, and we're going to say ReLU is equal to torch dot maximum between the x and torch dot tensor of 0.0. Okay, once we have that, we're going to put it into the second layer. So x equal to x at the weight of the second layer plus d2. But now, once we've done this, we don't want to put the second ReLU, because this is the last layer, this is the output layer. So actually we want to put in one of the activation functions that are for the last layer. So there are two different activation functions. The first one is the sigmoid, which is for binary classification, and this is not binary classification because we have 10 classes. This is multi-class classification, So we'll need to use the softmax. So let's just compute the softmax. So if you remember, it's xbx and then divided by x.xbx.sum. So basically we take e to the x and we divide it by the sum of e to the x, and this changes in normally we would have like logits coming in over here. You can actually probably print the x over here, then print x afterwards. We can break and we can see what we'll get as the output. So first of all, yeah, you can see the nans are pretty big because you can see these numbers are pretty big, but we're going to need to fix that. Seems to be a bug. So first of all, you can see that numbers come in here and then there's probabilities supposed to go on here, but let's quickly fix that bug. So let's just make e equals xpx is equal to x.xpx of and then we'll take that and we'll just do this instead, except we want to just make a bit of a change here, is that we're going to minus the max of this, and if you remember, that's just going to make it more stable. So if we run that again, okay, so I think what we did wrong here is that we're supposed to actually minus it before the xpx, so we actually have to do x minus x dot max of the xpx. So cool. Let's do that quick. So this should be fine, and then yeah, we have that, and that should work now. Should get a better result. Up, still an error. Let's see what is here. Okay, we didn't put the two brackets. Okay, cool. So yeah, we've managed to fix it now, but you can see that values are still pretty high, which is not good. That means we did something wrong in the initialization. So a trick what we can do for the initialization is we can actually divide by the square root. So square root of the thing that's coming in, of the number of neuron that's coming in, so square root of that, and then we can also just do the square root of this as well, 0.5. This will just lower the overall network output, and then this will make it more stable, and also it's based on the number of inputs here. But yeah, this is how they generally initialize fully connected layers. This is yeah, what they use in PyTorch as well. So let's just run this, and then you can see that our values, well, our logits is a lot better, and then you can see our probabilities are a lot better as well. So all right. Cool. So now that we have it working, this is what we'll label as the forward pass. Don't know why this is. Okay. Seems that like it's been indented by one. It's very weird. So this is our forward pass, and then let me just end forward pass. Hey guys, sorry, I'm gonna have to cut the video here. It's getting a little bit too long. I'll release the second part next week. I hope you guys enjoyed and stay tuned for the next part.